3,200 megapixels, and they were taken by the world's newest and largest telescope, which is in Chile and has just released its first set of pictures.
Somewhere high in the Chilean Andes, the largest camera ever built just photographed 10 million galaxies in a single night. 10 million galaxies. Not over months of careful observation, but in 10 short hours of testing. The machine responsible carries the name of a woman who spent her entire life proving that most of the universe is completely invisible. Now her telescope might finally photograph what she could never see. Vera Rubin's unfinished quest. Vera Rubin was 10 years old when she started staying up past midnight to watch stars wheel across her bedroom window in Washington, D.C. Her father helped her build a wooden telescope. Her mother let her skip sleep. By the time she was a teenager, she was mapping meteor trails on paper, tracking their paths with the obsessive precision that would later reshape everything astronomers believed about the cosmos. She applied to Princeton for graduate school. They rejected her because Princeton did not admit women to its astronomy program. The rejection letter did not even attempt to be polite about it. She went to Cornell instead, where she studied under the legendary physicist Hans Bethe. Then Georgetown, where she completed her doctorate while pregnant with her first child. At every step, men told her that women did not belong in observatories, that the night work was too demanding, that she should stay home. She ignored them all and kept observing. In the 1970s, Rubin began studying something that seemed almost boring: how fast stars spin around the centers of spiral galaxies. The physics appeared straightforward. Stars near the middle should orbit quickly, because that is where most of the mass sits. Stars at the edges, far from the gravitational center, should move slowly. This is how merry-go-rounds work. This is how solar systems work. This is how everything with a center of mass works. Except galaxies did not work that way at all. Rubin measured the orbital speeds of stars in the Andromeda galaxy and discovered something impossible. The outer stars were moving just as fast as the inner stars. They were whipping around the galactic edge at velocities that should have flung them into intergalactic space, but they stayed put. Something invisible was holding them in place. Something with tremendous gravitational pull that emitted no light, reflected no light, and interacted with nothing except through raw gravitational force. She called it dark matter, and when she calculated how much of it existed,
we see a lot of matter where we don't see very much light, and that has led to the concept of dark matter.
The numbers were staggering. Visible matter, the stuff that makes up stars and planets and people, accounts for only about 5% of the universe. Dark matter makes up another 27%. The remaining 68% is something even stranger called dark energy, a force that is accelerating the expansion of space itself. Put it all together, and 95% of the cosmos is invisible. We are not just missing some of the picture. We are missing almost all of it. Rubin had discovered that we are living in a universe made almost entirely of things we cannot see. She spent the rest of her life trying to understand this invisible architecture. She wanted to map where dark matter concentrated, how it flowed, how it shaped the structure of galaxies and the spaces between them. But the tools did not exist. Telescopes could see light. Dark matter produces no light. She could measure its effects, but she could never photograph it directly. She died in December 2016, still waiting. 3 years later, astronomers named the most ambitious observatory ever constructed after her. The Vera C. Rubin Observatory would do what she never could: create a complete map of the invisible universe by watching how dark matter bends the light from billions of distant galaxies. Her unfinished mission would finally have a machine capable of finishing it. Behind this effort is a colossal digital camera with an engineering design that turns Rubin's dream into reality. It captures details so fine and so vast that the universe may finally reveal the material she spent her life trying to understand. The engineering of the 3,200 megapixel camera. The camera at the heart of the Rubin Observatory is not like anything that has existed before. Engineers at SLAC National Accelerator Laboratory spent over a decade constructing it, solving problems that had never been solved, building components that had never been built. When they finished, they had created the largest digital camera in the history of science. The numbers almost sound made up. The sensor array contains 189 individual CCD chips, arranged into 21 separate units called rafts. Together, they create a focal plane 64 centimeters wide, roughly the size of a car tire laid flat. The total resolution reaches 3.2 billion pixels, making it the highest resolution camera ever constructed for any purpose. A single image from this camera would require 1,500 high-definition television screens arranged in a massive wall just to display it at full resolution. Your smartphone camera has maybe 12 million pixels. This one has 3,200 million. But raw pixel count is just the beginning. The camera can see a patch of sky 40 times larger than the full moon in a single exposure. It can detect objects so faint that their light has been traveling for billions of years. It takes a new image every 15 seconds, slewing across the sky with mechanical precision, photographing region after region after region without human intervention. To achieve this sensitivity, the sensor array must be kept at negative 100 degrees Celsius. Any warmer and thermal noise would drown out the faint signals from distant galaxies. Engineers designed a cooling system that maintains this frigid temperature evenly across the entire focal plane without creating vibrations that would blur the images. The whole assembly weighs over 3 tons, yet must be positioned with micrometer accuracy. The camera sits at the top of an 8.4-meter primary mirror, one of the largest ever polished for astronomical use. This mirror was cast from 20 tons of borosilicate glass, then ground and polished over 7 years, until its surface deviated from perfect by less than 1/millionth of an inch. The telescope housing rises from a mountaintop in Chile, 2,682 meters above sea level, where the air is thin and stable and the nights are exceptionally dark. Every night, this machine will photograph the entire visible southern sky. Every 3 nights on average, it will complete a full survey. Every image will be processed through automated pipelines that can identify changes, flag anomalies, and alert astronomers around the world within 60 seconds of detection. The data flow will reach 20 terabytes per night, roughly equivalent to downloading 10,000 feature films every single evening. Yet even with such astonishing power, a deeper question rises quietly behind the machinery. Watching the sky almost every night does more than gather new images. It changes the way the universe reveals itself. What makes Rubin different from deep telescopes? Every telescope ever built has faced an impossible choice. You can stare at one tiny spot in the sky for hundreds of hours and see incredibly faint, incredibly distant objects. Or you can sweep across vast areas quickly and build a map of the bright universe. You cannot do both. Depth or breadth? Pick one. The Hubble Space Telescope represents one extreme. Its famous deep field images required staring at a single minuscule patch for over 100 hours, patiently collecting ancient photons one by one until galaxies emerged from the darkness, like photographs developing in a darkroom. The resulting images revealed thousands of galaxies in a region of sky, smaller than a grain of sand held at arm's length. The pictures were breathtaking and scientifically revolutionary, but the method was impossibly narrow. At that rate, surveying the whole sky would take longer than the remaining lifetime of the Sun. Survey telescopes represent the other extreme. They photograph enormous swaths of sky quickly, building catalogues of millions of objects. But they cannot see faint targets. They sacrifice depth for coverage. Rubin breaks this trade-off by adding a third dimension: time. Instead of choosing between one deep image or many shallow ones, Rubin will take 800 images of every spot in the southern sky over 10 years. Each individual exposure is relatively brief, but stack 800 exposures on top of each other, and you get something as deep as the Hubble Deep Field, except covering the entire observable southern hemisphere instead of one tiny patch. The mathematics are almost absurd. By the end of its survey, Rubin will have photographed 20 billion galaxies, not million, billion. That is more galaxies than there are people who have ever lived on Earth. It will catalogue 17 billion stars in our own Milky Way, essentially creating a census of our entire galactic neighborhood. It will track the orbits of 6 million asteroids and comets in our solar system, many of which have never been observed before. It will detect 10 million transient events, things that flash, explode, move, or change in the night sky, catching cosmic drama as it unfolds. But the numbers only tell half the story. The real revolution is what happens when you watch the same regions over and over and over again. Traditional astronomy produces snapshots. You photograph a galaxy once, and you see what it looked like at that instant, frozen in time like a family portrait. Rubin produces movies. You photograph a galaxy 800 times over 10 years, and you see it live and breathe and change. Stars explode in brilliant flashes. Asteroids drift silently across the frame. Black holes flare suddenly as matter spirals inward, releasing jets of energy visible across billions of light years. Gravitational lenses shift as dark matter halos slowly evolve over cosmic timescales. And if Rubin is making a movie of the entire sky, then the most exciting question becomes clear. What kind of cosmic drama will unfold once the camera starts rolling? 10 million galaxies in 10 hours. In June 2025, the Rubin Observatory completed its first serious test run. Engineers were not trying to make discoveries. They were checking whether the camera worked, whether the data pipelines could handle the flow, whether the automated systems could slew and shoot and process without breaking down. 10 hours later, they had photographed 10 million galaxies. Think about what that means. Humanity had never photographed 10 million galaxies in any amount of time with any telescope. The entire catalogue of known galaxies before Rubin was smaller than what this camera captured in a single night of testing. The machine was not even trying to do science yet. It was running diagnostics, checking focus, calibrating sensors, and almost accidentally, it produced the most productive single night of galaxy observation in human history. The images themselves were stunning beyond expectation. Glowing nebulae where stars are being born appeared in exquisite detail, their gas and dust illuminated by the fierce radiation of newborn suns. Ancient galaxy clusters bound together by gravity and dark matter revealed intricate structures that hint at billions of years of cosmic evolution. Delicate spiral arms, traced by billions of individual stars, showed patterns that encode the history of galactic collisions and mergers. And at the very edge of detection, astronomers spotted faint smudges that are themselves entire galaxies, billions of light years away. Their light having traveled since before Earth even existed. But 10 million galaxies is just the opening scene. Over the next decade, Rubin will photograph 20 billion galaxies, each one captured hundreds of times. The statistical power this creates is unprecedented. Patterns invisible in small samples become obvious in samples of billions. Rare events that happen once per million galaxies suddenly appear thousands of times. Scientists will use this data to measure the distribution of dark matter across the observable universe. They will track how galaxies cluster along vast cosmic filaments. They will watch supernovae explode in real time, sometimes catching them within hours of detonation. They will discover classes of objects that no one has ever seen, because no one has ever looked at enough of the sky often enough to find them. The first test run was a proof of concept. The next 10 years will rewrite astronomy, hunting the invisible architecture. Vera Rubin proved that dark matter exists by measuring how fast stars spin. But she could never see where the dark matter actually sat. It was like knowing that a room contains invisible furniture by watching people bump into things without ever seeing the furniture itself. And if 10 million galaxies can appear in a single night, then one cannot help but wonder what hidden forces and unseen structures lie in the vast darkness between them, waiting for Rubin to uncover them. Hunting dark matter's shadows. The Vera C. Rubin Observatory carries forward the mission Vera Rubin could not complete in her lifetime. It works through a phenomenon called gravitational lensing. Dark matter has mass, and mass bends the fabric of space itself. When light from a distant galaxy passes through a region of concentrated dark matter, it follows the curved space, making the galaxy appear slightly stretched or warped when it reaches our telescopes. The distortion is incredibly subtle, far too small to notice in any individual galaxy. You would never spot it by eye, but measure the distortion statistically across billions of galaxies and patterns emerge. The dark matter leaves fingerprints everywhere. You just need enough data to see them. Those patterns are a map of dark matter. By analyzing the shapes of 20 billion galaxies, astronomers will construct the most detailed three-dimensional map ever made of the invisible structure of the cosmos. They will see the vast filaments of dark matter that connect galaxy clusters like threads in a cosmic web, highways of invisible matter along which galaxies slide and cluster. They will measure the halos of dark matter that surround individual galaxies like invisible shrouds, weighing them by calculating exactly how much they warp the light passing through. For the first time, we will see the scaffolding on which the visible universe is built. This map will test theories that have never been testable before. Does dark matter behave exactly as predicted by our current models? Does it clump in the expected ways at both small and large scales? Are there anomalies in its distribution that point toward entirely new physics, perhaps even requiring modifications to Einstein's theory of gravity? 50 years after Vera Rubin proved that dark matter exists, the data will finally answer questions that she could only ask. The invisible architecture of the universe will become visible at last. But dark matter is just one mission. Rubin will simultaneously revolutionize our understanding of our own cosmic neighborhood. Every night, the telescope will detect asteroids moving against the background stars. Over 10 years, it will catalogue 6 million asteroids, including hundreds of thousands that have never been seen before. Many of these will be near-Earth objects, asteroids whose orbits bring them dangerously close to our planet. Some could be potential impactors. Finding them is the critical first step toward planetary defense. You cannot deflect an asteroid you do not know exists. Rubin will find them. The observatory will also catch cosmic violence in progress. Supernovae, the explosive deaths of massive stars, will be detected within hours of detonation rather than days or weeks later. This early warning gives astronomers worldwide the chance to point other telescopes at the explosion while it is still young, capturing data that would otherwise be lost forever. Variable stars that pulse and flicker will be tracked across years, revealing patterns in stellar behavior. Strange transient events that defy easy classification will pile up in the data, challenging theorists to explain what produces them. What lies ahead for humanity? The astronomers who saw the first images in June 2025 struggled to describe what they felt. Jelko Ivesic, the observatory director, kept returning to sheer scale. One image covers sky equivalent to 45 full moons. Aaron Rudman, a SLAC astrophysicist, emphasized the speed. Millions of changing objects detected every single night. Kelly Hambleton-Persher called the detail mind-blowing. David Chuss noted that a single Rubin image contains more sky than most telescopes observe in entire careers. But perhaps the most telling reaction came from Henk Hoekstra, a cosmologist from Leiden. He described Rubin as a 10-year time lapse of the universe, with new frames arriving every few nights. The combination of quantity and quality, he said, is remarkable. This language matters. Astronomers have spent centuries taking photographs. They are about to start filming. The implications extend beyond pure science. All data from the Rubin Observatory will be publicly released after a brief proprietary period. Any astronomer anywhere in the world can access the full survey. A researcher in Ghana will work with the same data as someone at Harvard. A curious teenager with internet access could make a genuine discovery. This democratizes cosmic observation in a way that expensive space telescopes never could. The discoveries will come from everywhere, from anyone paying attention. There is also the profound matter of what we do not expect to find. Every major new telescope in history has discovered objects and phenomena that its designers never anticipated. The Hubble Space Telescope was built primarily to measure the expansion rate of the universe. It ended up revealing that the expansion is accelerating, driven by mysterious dark energy that no one predicted. Rubin is built to map dark matter and catch transient events. What it actually discovers may be stranger and more revolutionary than anyone today can imagine. Vera Rubin once said that she became an astronomer because she could not imagine living on Earth and not trying to understand the true structure of the universe. She spent her life proving that most of that structure is hidden. Now the telescope that carries her name will spend 10 years trying to reveal it. The camera has been warmed up. The mirror is polished. The data pipelines are ready. The universe is about to become a movie, and we are all going to watch it together. What do you think Rubin Observatory will reveal first as it turns the universe into a living movie? Share your thoughts in the comments and let's explore the unknown together.